Time to start integrating in polar and cylindrical coordinates. And I'm going to use the domains from the previous lecture. But first I need to talk about, what goes on when you're integrating in polar and cylindrical coordinates and the right way to think about a term that you're going to see in a moment. And in terms of polar coordinates and cylindrical coordinates, really what you should think to yourself is that these are like pre-baked multidimensional U substitutions. Okay, you learned U substitution hopefully at the end of your Calc 1 class. Certainly you did a lot of it by the time you were doing a bunch of integrals in Calc 2. Okay, and you were always busy, you'd search hard to find a good U substitution. The fact is that when you're in multi-dimensions, there are three sort of multi-dimensional U substitutions, or two in particular, I guess, that you use all the time: cylindrical coordinates and spherical coordinates. And we'll see spherical later this week. But in 2 dimensions, you also do polar a lot. Okay, so polar and cylindrical coordinates are like pre-baked U substitutions. And in terms of the fact that they are like pre-baked U substitutions, realize the following. When you are doing a U substitution, let's suppose that U is x squared. If U is x squared, then, does du equal dx? Well, I sure hope no one in Calc 3 thought the answer to that was yes. And I have quotes on the equal sign and on the du and the dx, because as far as I'm concerned, it's all very symbolic, but you know what I mean, and you know how this works when you do a U substitution. What you're going to do is you're going to view du as being 2x dx, right? You're going to take the derivative of the x squared. You're going to say, okay, du is 2x dx. And so I have the same kind of question now where I say, does dx dy equal dr d theta? And hopefully you can guess that the answer indeed is no. It's certainly not, okay? And that's sort of it's a very basic error. If you think, if you do in an integral, if you put dx dy equals dr d theta, that is the Calc 3 version of the error of saying that du is dx for this nonlinear, non-trivial U substitution. In fact, dx dy, or dA if you prefer, is r dr d theta. Okay? There's that r term. Just like over here there's 2x, down here there's r. And you can say, well, how do we calculate it? Where does it come from? And I may make a video later on about that. But the answer is that as far as you're concerned, it's certainly something that you memorize. Okay. How about cylindrical coordinates? Well, in cylindrical coordinates, very similar thing. Dx dy dz, or any dv if you like, becomes r dr d theta dz. Although the dr d theta dz can be in different orders, r dz dr d theta, etc., whatever order makes you happiest. And now I have done something extremely subtle. I suppose that in the argument I had with somebody online last night, this brings back fond memories. So there you go, all caps. You must always remember that r when integrating in polar and cylindrical coordinates. Okay, it's a huge mistake and a very common one to leave off the r that belongs here. This r right here. If you leave that out, you are doing a bad thing. Okay? This thing right here. Okay, and so that's really all I have to say about this that you really need to know before we start doing integrals. Okay, and so let's now do some integrals. And so let me recall some of our domains. And I've given them names now. I call this guy D1, okay, this guy D2. So let's take D1 and let's do a couple of integrals on it. So let's suppose I want to integrate over D1. I want to integrate, let's do y dA. And then in a few moments, let me integrate, how about, and again over D1, let's go with 1 over x squared plus y squared dA. Okay, so 2 integrals to do on this d1. Well, what does this equal when I look at it in polar coordinates? Well, I've done a lot of the heavy lifting already. R goes from 1 to 2, theta goes from 0 to pi. So I can really write that down more or less straight away. R goes from 1 to 2, theta goes from 0 to pi. What is y in polar coordinates? R sine theta. R sine theta. And now, what would be wrong? What would be wrong would be to write dr d theta. Why is it wrong? Well, what was the thing in bold? Don't forget the r. This r right here. Absolutely positively necessary. Okay? It's like you're doing a u substitution. It has that extra term. Okay, so this is actually going to work out fairly quickly. I didn't give myself much space because I don't need it. Theta goes from 0 to pi. I have r going from 1 to 2. Sine theta doesn't depend on r. I can pull it out. And now I have an r squared dr d theta. And let me think about this a moment. R cubed over 3, 8. This one's 7/3. I think it's 14/3. That's my guess thinking about this. So you can let me know if I'm right. What's this? This is an integral. Okay, it's the same region. So r equals 1 to 2. Theta equals 0 to pi. This is a 1 over r squared. R, gotta remember it, dr d theta. Okay. Well, it's completely independent of theta. Theta goes from 0 to pi. That's going to be pi. This is a 1 over r. I'll get a natural log from 1 to 2. Natural log of 1 is 0. Pi natural log 2. Done. Okay, let me do an integral over d2. Okay. And let me integrate x over d2. Okay, so somebody comes along and says, let me move this. Oops, I know what I'll do. I'll fold it. Someone comes along and says, let's integrate x over d2. They basically give me this problem. d2, x, dA. Now, you could do this in regular Cartesian coordinates. It's actually both a type 1 and a type 2 region. It's not going to be a lot of fun because you're probably going to walk yourself into a trig substitution. Maybe you'll get away with a regular substitution. But let's see how easy this is if we do it in polar coordinates. In polar coordinates, I see r is going from 0 to 1. Theta goes from minus pi over 2 to pi over 2. X is r cosine theta. And now I suppose the hardest part of this is remembering, yes, you need the r. R dr d theta. Right? You cannot forget that r. Okay, so what is this? Well, I have an integral from minus pi over 2 to pi over 2 of cosine theta d theta. If you like, you can write it as a product altogether. R equals 0 to 1 of r squared dr. 1/3. I think it should be 2/3. Great. Another integral. Now let's do cylindrical coordinate integration. Integral over omega. And oh yeah, I was thinking I have a funny story I'll tell you when I'm done integrating over this omega. I know you all complain about Greek letters. But okay, I'm going to integrate over omega. Why don't I just integrate, how about z squared? Let's integrate z squared over omega. what's going to happen? Well, where do I want to do this? Here's a good spot. It's a triple integral over omega. And I said I want to integrate z squared. Why? Why not? D volume. Okay, so what is this when I write it as an iterated integral in cylindrical coordinates? Well, the z evidently goes from 0 to 2 plus r squared. If I stick that on the innermost integral, then after I do that, the shadow, if you will, is just this disk down here, which is this rectangle in r theta space. Oops, you can't see the rectangle. This rectangle in r theta space. So, r goes from 0 to 2. Theta goes from 0 to 2 pi. I have z squared in my thing, and I have to say r dz dr d theta. And that is, again, the r I must not forget. So, anyhow, this is not going to be terribly exciting, but let me start it at least. R equals 0 to 2. Let me pull this r out of the z integral. And now I'm going to get z cubed over 3. Oh, this is going to, I think I'm going to definitely, z equals 0 to, oh, you know, there's a clever way to do this. 2 plus r squared. dr d theta. I can write this now, well, okay, let me. Theta goes from 0 to 2 pi. R goes from 0 to 2. R times 2 plus r squared cubed over 3 dr d theta. And I'll leave this as an exercise, but the theta integral you can do as a product with the r integral. I mean, it's just going to give you 2 pi times the r integral. And for the r integral, rather than cube this whole thing out and do this all in its awfulness, do a u substitution. U is 2 plus r squared. That will make your life warm and happy, because this r you'll absorb as part of the dr. In any case, my silly little story related to Greek letters is I had a former PhD student who was incredibly proper and always used to insist on calling me Dr. Blank, and was just very, very proper at all points. And we get to capital gamma, this Greek letter, and I always refer to it as the Greek letter hangman. And you know, and him being so proper, it took him a while before he was finally calling it the Greek letter hangman, or, you know, integrate with respect to hangman or over hangman or whatever. And then he's finally saying this, but then he has this test, this oral exam in front of all these professors, and this capital gamma keeps coming up in his lecture, and every time it comes up, you can see there's this pause, whereas in his head he needs to reroute the neurons from him saying, you know, integrate over hangman, or, you know, whatever it was with respect to hangman. So anyway, that's just my little silly story about my proper PhD student who finally started referring to capital gamma as hangman. Okay, and anyway, there will be more integration to come and spherical coordinates soon. Okay, take care.